All right, let's keep talking about derivatives. My goal is that you see some of the fundamental rules here in this first day, and you even realize how you can use these rules to find some slopes and to find some tangents. Honestly, the same stuff you were doing with a limit not too long ago, I want to quickly show you that we have this kind of new and improved method. Again, it's called a derivative, and it ends up being some rules. Now, the way I kind of do this is I'll put the rules up here, and then if there's an example that can go with it, I'll use the chalkboard. Honestly, some of the rules we just talk about. We just say, hey, there's the rule. There might be something you want to write down. I just don't want you to get bogged down and be like, do I have to memorize, rule 1, rule 2? You don't. You're going to realize that all the rules pretty much go together anyway. So here's the first one. We'll call it the constant rule. Rule 1 for a constant function. Like I said, you can write that down if you want. What I really want you to do is think about how to do a constant. So what I'm going to do is supply an example of a constant. Now, sometimes constants can be tricky because there's not much to them. I remember when I taught ninth graders Algebra 1, it seemed like these problems gave them more trouble. Remember, y equals 5 is a line, but it's a special line. Are you picturing a horizontal line? Okay, so picture a horizontal line. But you're in calculus class. So what we do is we find the slope of that line. Okay, now you're picturing a horizontal line. The slope of a horizontal line is always 0. Thank you. It's always 0. That's the constant rule. The constant rule says that the derivative, now I'm using some notation here. You'll get comfortable with it. So if y equals 5, then the derivative is, always 0. Okay, because again, the slope of a horizontal line, you already know that, is always 0. Okay, so that's the constant rule. The power rule. Now, this is the one that we previewed. This is the one that required or allowed you to change the exponent. This is the one where if I have x to the n, then you can bring n down in front and subtract 1. You'll learn this. It's kind of the most fundamental rule. It's how you can think about the slope when you have a power. Okay? It's how you can think about the slope when you have a power. Now, to sort of drive this home, to make sure that you realize just what you've now been given, we're going to spice up a little bit. Functions that you're more used to looking at that have multiple terms. So 3x to the 4th, x squared, minus x plus 4. Again, try to get comfortable with the notation as soon as possible, which you will. And this is because it's f of x, I'm writing as f prime of x, which means the derivative. Now, this power rule, very, very powerful. Okay, you can bring the exponent down. Now, when that 4 comes down, what do you think it's going to do with the 3? When they meet, you're going to multiply. Okay, so I'm going to do that right away. That 4 meets that 3, it's going to multiply. You subtract from the 4. Now you get x to the 3. As we continue down the path, though, we encounter x squared. Now, x squared, we did that one. Of course, it's going to be 2x. But if you use the little power rule, that's because the 2 comes down and you subtract 1. Next, you get to x. Again, sometimes it's these simpler ones that can be a little tricky. Okay, if you want to think of it as x to the first, that's fine. Okay, because then you can bring a 1 down in front. What happens when you subtract 1 from 1? Obviously, you get 0, but what happens as an exponent of 0? It would just become 1. Are you seeing like a bunch of 1s? There's a 1 that came down in front. There's a 1 that came from the exponent of 0. So when all the dust settles, you get minus 1. Now, there's another way that you could say, Ms. Naylor, it's negative 1. What I mean is there's another way that you could look at that and say the slope is negative 1. I just gave it away, right? How do you look at that and say the slope is negative 1?
Negative x.
And what is negative x? Okay, maybe I'm making a big deal out of nothing here, but we just want to make sure we understand that back in algebra land, this had a slope of negative 1, and it still does in calculus. Okay, so that's y equals mx plus b. That's still the slope. All right, 4, the derivative of 4. You mean the slope of 4? Yeah, it's the same thing. Oh, 0. We just figured that out with the constant rule. Now, normally you don't write plus 0. I'm going to erase it now, but we end up with our derivative. Now, that's nice. It's supposed to make you feel like you got it. What I'm going to do now is ratchet it up a few notches and see if we can apply the same rule to this big bad function. This is a problem that I hope that you look back at, because what I actually did here was probably put in about 3, maybe 4 of the most common mistakes. I mean, there's 4 terms here. There's almost like a common mistake on each of these terms. Okay, you can understand this even though it's still the first day, but I just know that the mistakes that are common as we go through this chapter go back to this problem. So listen up. Let's see if we can get this right the first time. Okay. First of all, the number in front of x is not really 2, but 1/2. I know you guys know that, but make sure that you're comfortable that there's a 1/2 that's going to meet this 6. I mean, you can also think of it as dividing by 2. Obviously, that's the same thing. So the 6 comes down, it gets divided by 2, it becomes 3. Now, if you subtract from the exponent, you get 5. I don't know if there's really a common mistake on that one, but I do know that there's a common mistake on this one, because suddenly when things are negative, people change the rules. Don't change the rule. Bring the exponent down. Subtract from the exponent. Okay, and this is the part where be careful, because I know we all know how to subtract from negative 3, but on a bad day, people tell me that that equals negative 2. On a good day, you would tell me it equals negative 4. You have to subtract from the negative exponent. Next, this guy. Now, this will be something that sometimes becomes kids' arch nemesis for the whole year. And quite simply, it's because you can't do the derivative when it's in this form. It's not like a power function. It's actually a rational function. A rational function is a fraction. Here's the good news. All you have to do is think of this as a power function. How do you think of it as a power function? You apply a simple exponent rule from other years, and we even reviewed it this year. Now look what I did here. I interpreted an exponent in the denominator as a negative exponent. I interpreted an exponent in the denominator as a negative exponent. Now, there'll be a time where you guys start to do that in your head, but maybe it's something you want to write out off to the side, because 2x to negative 2 is what I'm going to do the derivative. Of course, using the rule, you would get negative 4x to the negative 3. Okay, negative 4x to negative 3, when inserted back in here, is going to also change me to a plus a positive, so we might as well change it. But I really want you to focus on the new exponent. The new exponent is negative 3 because you had to interpret this original problem as a power function, basically as a negative exponent. And then we get to this last one over here. And again, I tried to put some common mistakes into one problem, and honestly, this is wrong. This is wrong. Why can't I bring down that exponent? I thought that was kind of what we were talking about. Why can't you bring down that exponent? It's a little detail up here, and sometimes it's missed. Okay, but simply,
There's no x there.
yeah, there's no x. Okay, x to a power is a whole lot different than a number to a power. Well, what is a number to a power? What is a number? It's a constant. Okay, not that I'm trying to fool you, but don't be fooled. This is just a number. What's the slope of a number? 0. 0. Normally we don't write 0. I'm just writing it so you can see that we did it correctly. You can erase it if you want. I'm going to leave it there for effect for now. Now, I know we went a little bit slowly. I told you there's some common mistakes in this problem. The other thing is, negative exponents are not proper. They're not technically supposed to be part of a final answer. So what do? We flip them back over. Now, I'm kind of squeezing this down at the bottom, but this is 3x to the 5th minus 3 over x to the 4th plus 4 over x to the 3rd. And now we'll leave off the 0. But you really do need to flip back to a fraction. You're not allowed to have an answer with a negative exponent. Okay, why not? I don't know. It's part of math etiquette. Math etiquette says no negative exponents. Okay. Now, these two rules we just did, but I still want to display them. You'll see them in the book, and I just kind of want to officially say that what we just did, we're allowed to do. So what did we just do? We probably didn't even really think much about it, but technically, when there's a coefficient, like 3, like 1/2, okay, any of the coefficients that were in these problems, you can see that they just got multiplied. Again, if you have a coefficient like 3 or like 1/2, it just multiplies. And then a polynomial, honestly, every problem that we've done up here is a polynomial because it has multiple terms. The polynomial rule says that you're allowed to do the derivative of each term. You didn't really think about it because I just started doing it, but it works. You're allowed to do the slope of each term and basically come up with a final answer. I like to call that sometimes calculus common sense, okay, because it just makes sense, okay? But it is a rule, and you're allowed to do it. Let me just see here. We're definitely going to do this problem. Actually, I think I have it up on the screen here. I do not. So let me write this out. I want you to see this language. It's kind of where we started this afternoon. It's also going to be kind of like where we end. So we're going to find the slope of a tangent. This time I'm giving you an x value. So at x equals 2, and then the equation is 2x squared plus 1 over x. Make sure you don't miss this. If you do, then I did a really bad job of teaching it, or maybe you just were zoning out. The slope of a tangent is the derivative, but we have a new way to do it. You don't need to plug into that limit formula. You actually can just do the derivative rule. You can follow the rules. Okay, so we kind of have this new and improved way to attack this problem. It's not supposed to be that hard. You just do the derivative, you bring the 2 down, you get 4, you subtract from the exponent, you actually just get an exponent of 1. So we have 4x. Now, you can thank me later, and usually kids start to get the idea, but whenever you have a fraction, you got to think as a negative exponent. I'm telling you, you have to think of this as a negative exponent in order to do the derivative correctly. Okay, so when I do the derivative of 1 over x, what I'm really doing is the derivative of x to the negative 1. So we bring down negative 1. When you bring down negative 1, you get negative 1x or negative x. And then when you subtract, you get negative 2. Again, be careful about these fractions. I keep bringing them up because they sometimes become people's nemesis. Now, this derivative is a slope formula. Slope formulas are nice, okay, because you can plug into them. Oops, I'm getting one step ahead of myself here. We really should clean up this negative exponent. Okay, when you have a negative exponent from your algebra class, from the stuff we reviewed this year, you can flip that back over to be a positive exponent. So I get 4x minus 1 over x squared. Now listen, when you have a formula, you can plug into it. Okay, this is nice. This is why this is easier. So we're going to plug in 2. Make sure you realize the reason we're plugging in 2 is because that's the x value that was asked for. But do it. Go for it. You can plug in 2. Understand that the answer you get, 8 minus a fourth, 7 3/4, or the fraction equivalent, that's the slope. Okay, to be more specific, that's the slope of the tangent. And to make one more little connection, like you did in the last chapter, wasn't too long ago, it's actually describing a graph. Now, I want you to see what I'm typing in here. It's just kind of a little extra for this problem, but I'm typing in the original function. Okay, I'm not typing in the derivative. I'm honestly just typing in the original function. I wouldn't expect you to know what this looks like. I'm even trying to remember here with a Zoom standard. Okay, we kind of get this. Let me interpret that a little bit. It's actually a graph that it's got some business, some funky business going on. But ultimately at x equals 2, which would probably be like more like over here, at x equals 2, there's a tangent line. And that tangent line has a slope. And that slope is 7 3/4. Now, this is big stuff around here. You guys will learn that this whole idea about slopes is one of the branches of calculus. I alluded to this some time ago, but calculus ultimately there's a calculus tree, okay? And kind of at the root of the tree are limits, but limits got us to this branch already. It's the derivative branch. And so we'll be talking about this idea of a derivative for quite a while. The reason we talk about it for quite a while is because there's so many functions out there. The only functions we've done so far are kind of simple ones, okay? Basically powers and numbers, but there's other functions, okay? In case you're curious, there's trig functions. In case you're curious, there's functions that involve exponents. We call them exponential. And so there's a lot to talk about. But right now we're just getting sort of the tip of the iceberg. But I want to make sure you realize that it always goes back to this, okay? A tangent line. And I'll be sure to show you why tangent lines are so special. But we got to save something for the next time. So we'll do that next time we're together.